First thing we're going to talk about with light is understanding how light moves. Fundamental to how to control light is to understand how it actually moves. So we're going to start out with a light source. And it could be any source. We could take the sun as an example, or we could take the moon, or a candle, or a tungsten light fixture, or any light source. That light source is generating tons and tons of photons, these particles that are traveling in waves out of that light source and towards a subject, towards whatever. There's a beam or this column of photons that are streaming out of that light source and moving in whatever direction. Now with the sun, it's basically omnidirectional. It's going in every direction, but we don't see all those because we here on the earth, we only see the beams that are coming directly towards us. So light moves in a straight line, always in a straight line. Once it starts out on a path, it will never vary until it hits something. So it doesn't spray around, it doesn't move in all sorts of curves and whatever. That light is going to travel in a perfectly straight line. And largely when we're dealing with a light fixture where we're trying to cast light onto something, it's going to be moving in a largely parallel block. It's not necessarily going to be absolutely perfectly parallel, but the light's going to be mainly moving in generally the same direction. All these things are kind of important for us to understand because as we know how light moves, that gives us power to be able to control it. And the first thing that we learn when this light is moving is that it'll continue in this straight line until it hits something. And when it hits something, basically two things are going to happen. One, it's going to bounce. And two, it may take on some of the color properties of whatever it hit. We'll worry about color in a minute. But as the light travels, it's going to travel in a straight line until it hits something, and then it's going to bounce off of that object. And that's kind of key, because we can only see something if light comes down, hits it, and then bounces off that subject and into our eyes. We don't see out of our eyes. What we see is what light comes into our eyes. And that light bouncing off a subject, landing on our retinas, lets us see that object. And it'll usually bounce off directly at the angle of incidence will equal the angle of reflection. Just like in a pool table, how the ball bounces with that specific angle, the same thing is going to happen with light. If you're dealing with a perfectly mirrored surface, that's exactly how it'll work. A perfectly polished, perfectly smooth surface will reflect those light beams exactly as they have arrived. So if you shone a light directly into a mirror and had it bounce immediately directly out of that mirror, directly back at you, you would get pretty much close to 100% of the light coming back right at you. Very few items in this world are perfectly polished mirrors though. So usually what will happen is if you examine any surface that something's going to hit and you get down really on the microscopic level, it's not perfectly polished. There's going to be little pits and valleys and texture. And so when the light hits those pits, it's going to bounce in one direction. When it hits the valleys, it's going to bounce in one direction. When it hits the peaks, it's going to bounce in a direction. So when light hits any particular object, it's usually going to scatter to some degree. And the degree of scattering is going to be based on what the texture of the surface is. We can use this to our favor by bouncing light off of a certain surface and having it diffuse if that's the way we want it to go. Or we can use it to bounce light off a perfectly mirrored surface if we want to maintain as much of light intensity as possible. Now, another thing to factor in as light travels is that because it's not traveling in a perfectly parallel path with all the other photon beams, any light source is not putting out a beam of light. It's putting out billions and billions of photons worth of light, each and every one of those little particles contributing to the overall effect. But they're not all traveling perfectly parallel. So as the light travels, they're eventually going to spread apart and they're going to gain a little bit of distance. And as they spread apart, they're going to lose intensity. That light is going to be less intense the longer distance that you ask it to travel. Now, the second thing we're talking about is when light hits an object, not only does it bounce, but it also may take on the properties of the object that is hit to the point that it may actually be absorbed. Let's take, for an example, a perfectly black source. If that light moves and hits a black source, then that light photon will basically cease to exist as light. It will instead be converted into heat. So if you shine light onto something that's white and it reflects all that light back off of it, that white object won't get very hot because it's not retained any of that light. And you'll get a brighter light coming off of it. But if you shine that same light into a black surface, that black surface will suck up the light. It'll soak it up. It will convert the photons into basically heat, and they'll cease to exist. So this is kind of a way you can vacuum up stray light out of your scene and not have it bouncing around, scattering everywhere, filling in where you don't want it to go. You can control that light by sucking it up with properly placed black flags or using barn doors, black barn doors that will block the light from coming out, but not just block it, actually absorb it. If you used white barn doors, that would just cause bounce light everywhere, spill light happening everywhere, because it would bounce off of those barn doors. The reason we use black barn doors is because it will absorb the light and keep it from going where you don't want it to go. What we're talking about now is really fun. This is a fantastic thing to learn about, so please stay awake, pay attention, don't hit the skip part on your DVD player. Listen to this part because this is how you really gain control over your lighting instruments, okay? What we're going to talk about here is the inverse square rule. Okay, now go back, pay attention, wake up, and don't give up on this because it's good stuff. The inverse square rule lets us understand how light intensity interacts with, now I said stay awake, okay? How light intensity interacts with the distance of a light source. What I'm really getting at here is you can get infinite levels of brightness out of any individual light source just by how close you move it. I can get brightness down out of any light source or get it up out of any light source just based on the position, and you can easily understand how the position affects things. So yes, I'm sorry to tell you, we are going to go into a little bit of math. It's not going to be scary or bad. It's going to make a lot of sense, so please pay attention, because after you understand this, you understand how these light fixtures can be used in infinite combinations. So let's examine the situation where we have a square light source and it's broadcasting its light onto a wall. And say a light is 1 foot away from the wall and the amount of area it's lighting up is 1 square foot. That's just, how the light spreads. It lights up 1 square foot. What will happen if I double the distance to the wall? Let's move that light source to where it's twice as far away. What happens to what gets lit up? It quadruples. It doesn't double. We're not getting twice the area lit up, we're getting 4 times the area lit up. Why? Because the area, instead of being 1 foot wide, now it's 2 foot wide. That is double, yes, but it's a square. So we're doubling here too. So now I have 2 by 2, I'm lighting up 4 square feet worth of area with that one light. That's the relationship. I've increased the distance by 2, I've increased the area by 4 because 4 is 2 squared. Now, if I double the light again, I'm at 2 feet now. If I go to 4 feet, now the area that I'm lighting up is now 16 square feet. It's 4 foot wide. We've doubled the width and the height. So now the area is 16 square feet of illumination from this light that we've just doubled the light source. So I doubled again, and it's now 4 times as much area. It's lighting up a bigger area, but it's having to spread the same amount of light energy over that bigger source. We haven't added light power, so we got the same amount of light that was lighting up all concentrated in 1 square foot is now having to cover 4 square feet. It's cut in intensity to 1/4. And when it goes to 16 square feet, it's cut intensity again to 1/4 of what it was. We've cut the brightness of the light by moving it further away. And the reverse is also true. If I have a light that is lighting up 16 square feet, and I cut the distance of that light to the subject in half, now it's going to light up 4 square feet. All that same energy that was spread out among 16 square feet is now concentrated on 4. And if I cut the distance in half again, it will now spend all that energy on 1 square foot and become that much brighter. So if you know what we're talking about in this situation, we're talking about the amount of intensity changes based on how much distance we've added squared. So now let's take the example of wanting to double the intensity of a light source. I know that if I cut the distance in half, it'll become 4 times stronger. I don't want 4 times stronger, I want 2 times stronger. So how much do I move that light source? Let's say it's 10 feet away, and I want to move it to where it's doubled. I can't go 5 feet because that will be too strong. So actually I end up going to 7 feet. I move it to where it's about 30% closer, and now it will be twice as strong. Maybe it makes more sense to go the other way. If I have it at a certain brightness and I want to cut that brightness in half, I can move it 40% further. I don't double the distance, I go 40% further. Why? I've moved it 1.4 times as far as it was. 1.4 is the square root of 2. So if I take 1.4 times 1.4, round it off a little bit because it's really like 1.42, round it off, we get 2 square feet. So if I move the light 40% further, it will cover twice the area with half the brightness. So what does this mean? If I'm in a lighting situation and I've got these 2 lights here and the director of photography says, that light's too strong, I want you to cut that light in half. How do you do it? You could put a one-stop neutral density gel in there, or you could use a dimmer, or you could just grab the light and move it 40% further. Just 40%. That will cut the light intensity in half. And if you want it to get stronger, if you want to double it, then you move it a little bit closer. How much closer? Not half. Half would quadruple it. The actual number is you want to move it about 30% closer. Or to look at it the other way, you want to move it to 70% of the distance that it was. So when we doubled the light, we moved it to 40% more distance, or 140%. What's half of 140%? 70%. So there's our 3 numbers. 1, and then if we make it brighter, we go to 0.7, and if we make it dimmer, we go to 1.4. What this really means is, let's not get too hung up on things, but if you move it just a bit closer, 30% closer, you will double the brightness. That's pretty cool. And you move it 30% closer again, you'll double it again. And 30% closer again, you'll double it again. You could be 8 times brighter just by moving it in those 3 times. Or, same thing, moving it away. So this is a really simple way to get nearly infinite brightness out of any given light fixture. By moving it closer or further away, if you know the numbers, which are 0.7 and 1.4, and you don't even really have to worry about remembering 0.7 because it's half of 1.4, so you really only need to remember the 40%. Now you have the ability to double or cut in half any particular given light source. You may have seen these numbers before, the 1 and the 1.4. What we're really talking about is manipulating the stops of light that we're working with. Now when you're on a set and the director of photography may call out and say, hey, bring that light up a stop. That means that he wants twice the light output there. A stop is a measurement of the amount of light. And when we increase the amount of light by 1 stop, we're talking about doubling it. And we talk about cutting the amount of light by 1 stop, then that means that we're cutting the amount of light in half. And the square rule applies again. So if we change the light by 2 stops, we're actually quadrupling or cutting the light into 1/4 as much. The same kind of things are going to apply. So let's look at a lens. Let's look at a lens iris barrel and look at these numbers that you see. 1.4 right there. Oh, look at, there's the 2. What is the 2 all about? Oh yeah, the square rule. The square root of 2 was 1.4. 1.4 squared is 2. You'll see the same relationship plays out in your lenses as it does in working with light, because lenses are stopping a certain amount of light from coming in. The lens has an iris in it, and the iris is this aperture that opens or closes as you specify. We refer to the measurements of that aperture in terms of f-stops. And the idea that I like to look at it with is that f, whatever f stands for, focal length or whatever we refer to it as, the f-stop is the closing of the iris such that it stops a certain amount of light from coming in. So let's take an example of f1. And when you see the notation of f1, it actually looks like f divided by 1. And that's pretty important to think about, right? Because it is actually a fraction. I'm sorry, there's more math, but it's easy. F divided by 1 means it's pretty much going to let in as much light as it possibly can. So what is f divided by 2? What if we go to f2? Well, the diameter of the iris has been cut in half. But that doesn't mean it's going to let in half as much light. It's going to let in 1/4 as much light. Because when you cut the iris in half, it's actually only allowing in 1/4 as much. The same reason as the inverse square rule. So if you want to cut the iris down by 1 stop, you want to make it 40% smaller. 1.4, right? So that's why the first number on your lens, if you have a really fast lens, it might be f1, and the next number is f1.4. And then what's 40% more than f1.4? f2. 1.4 times 1.4 is 2. So now we have f2. And 40% more than that? 2.8. 2.0 times 1.4, 2.8. Every f-stop is 40% more progression. So you can see that this same relationship, this same 40% smaller or 30% bigger. If we take f4 and we take 70% of that, what do we get? 0.7 times 4 is 2.8. f2.8 is one stop bigger than f4. So there we see the same relationship, 0.7, 1, 1.4. To go bigger, you want 70%. To go smaller, you want to increase by 40%.
One of the important things to remember about light is that different types of light actually put out slightly different colors of light. And to your eyes, it pretty much looks like it's all the same white light, but it really isn't. Your brain's really good at filtering out differences between different types of light and making everything look like it should. But a camera can't do that. A camera sees what it sees, and there's a slight difference in color to all sorts of different kinds of lights, which all basically look like white light to us. And what does color temperature refer to? Why is it called color temperature? That's not because the color has an actual temperature that you can feel. What it actually refers to is the color that a block of iron would acquire when it's heated to a particular temperature. And that temperature is measured in Kelvin. Kelvin is basically a Celsius degree, but it's measured all the way from absolute zero instead of the freezing point of water. But at 3200 Kelvin, a block of iron is going to take on an orangish reddish glow. And that is 3200 K, or you might hear it referred to as 3.2 K. It's referred to as tungsten or indoor lighting because oftentimes when you're shooting indoors, you're shooting with tungsten lighting. It has basically the same color that that block of iron would take on at that temperature. So when you hear of tungsten lighting, that's what it's referring to, kind of an orangish reddish glow. Now, daylight is basically sunlight, and when you look at the sun, it kind of looks yellow. But look at the sky. The sky's blue. And the sky's blue because there's all this blue light being reflected. Daylight is actually kind of a bluish color. So what color temperature is daylight? It's a little counterintuitive because you sort of think that if a block of iron were to get hotter and hotter, it would get redder and redder. But that's not really what happens. It actually gets red, and then that's the coolest hot temperature that it has. And then as the temperature gets higher and higher, it goes through the spectrum through yellow and green, and then it gets into blue. And blue is actually much hotter than red. Blue is around 55 or 5600 K, and that's what you'll hear referred to as daylight temperature, 5.6 K or 5600 K, because it's approximately the same color that block of iron would be at that temperature, Kelvin. Now, you can see it for yourself if, say, you are in a bathroom, and a bathroom has no windows, and you've got basic standard light bulbs in the lighting fixtures, and those are all incandescent bulbs, and they all have that tungsten or 3200 K color temperature. But suppose you have a white door to that bathroom, and it's open a little bit, and in the next room, sunlight's shining in through the windows. Well, if you look at that white door, you're going to see that it's taken on a blue cast because your eyes are adjusted to the orangish light of the incandescent lights in the bathroom. So if you look at that door, it's going to look kind of bluish. Now remember, when you white balance a camera, what you're doing is you're pointing the camera at something white, so it's reflecting the lights that you're using, and it will be reflecting the color temperature of those lights. And then you hit the white balance and it will adjust the camera so that that object actually looks white under the color temperature of that light. But if you're using lighting fixtures of other color temperatures, say you white balance for tungsten and you're using some daylight colored light, well, when those daylight colored lights shine on that white piece of paper, just like the bathroom door did, is going to look very, very blue. And that is the difference between color temperature. So you want to be real careful about the kinds of lights that you have. Because if you're mixing lights of different types, say you're mixing tungsten lights and you're mixing HMI lights. HMIs are daylight balanced, and we're going to get into all this when we actually get into discussing the lighting fixtures. But if you're using lights that have different color temperatures, you could end up getting a pretty ugly image, because you could be lighting from one side with orangish light and lighting from the other side with bluish light. And if you're looking at it with your eyes, you don't have any problem with it. Camera's not going to be able to deal with it. It may not look good, and that is what we call color temperature confusion.